Okay, so in the last video we derived the first kinematic equation of motion, v equals v naught plus at. We did that using these two equations, using calculus, knowing how if we have some kind of object in some kind of system, how might we describe it with variables, and how might we use math to turn that into an equation where we could solve interesting problems, like how much time it takes for an apple to fall, how far a box is going, that type of thing. But I kind of cheated a little bit. I calculated the 10 meters. I used an average velocity equation. I didn't derive that. I just told you what it was. I don't like that as much as showing the derivation. The other thing to think about is that the derivation for v equals v naught plus at didn't even need calculus. You can just think logically through this equation and it makes sense. You could just draw it up in your head like Isaac Newton drew up F equals ma or any other equation that he just made up and tested against the real world, and it turned out to be true. So v equals v naught plus at. So a final velocity is equal to the initial velocity plus an acceleration times time. If you're in a car and you're going 0 miles per hour, v naught, then your final velocity is going to be your acceleration times the time you take in accelerating that time. So if I'm accelerating 1 meter per second and I accelerate for 3 seconds, then 3 times 1 meter per second is 3 meters per second. That's going to be my final velocity after 3 seconds. Or you can think if I'm going 60 miles per hour already, this box is already moving in some direction at a certain rate of speed, that's the initial velocity, and then if I accelerate at 3 meters per second or something, then each second multiplied by time, that's how much speed I'm adding to my velocity. So it makes simple sense. Anyway, let us derive this second equation. So we'll start with v equals dx dt. And recall that we just made an equation to solve for v. So v naught plus at equals dx dt. Alright. In that case, we can say that this is a d, not an a. And see that v naught plus a t dt is equal to dx. Let's integrate both sides, and we have this going from 0 to t, and this is going from x naught to x. Then we're going to get an equation, v naught t plus half a t squared is equal to x minus x naught. And that right there is your second equation of motion. See all the steps of this? Again, we're integrating with respect to t, so v naught is a constant. Integrate, it's v naught times t. Now at, so a is a constant, but t is the variable here, so the integral of t is going to be half t squared, so half t squared times a, and this is equal to x minus x naught because we have 1 times dx, so the integral of 1 dx is x, and x minus x naught is what we have on this side. So that is the derivation of the second equation of kinematics. Let's clean this up a bit. And redraw it. So second equation is x equals x naught plus v naught t plus half a t squared. And so now you can see that if we wanted to calculate this was indeed 10 meters without cheating, we could say that For our example up here, our v naught was 0. This goes to nothing. And then our a, again, was 5 meters per second. So 1/2 times 5 meters per second times the t squared. We had t that was 2, so t squared is 4, is going to be equal to 2 times 5 equals 10. So x minus x naught is equal to 10. That is, the distance equals 10, and that matches the value we got initially. So this equation got us the same answer. Everything checks out and things are looking good. We can do the apple problem again if we would like. I would like to. I'll delete that. So if I want to know, say, the distance the apple travels, I can say that the v naught is equal to 0. So let's draw the equation up again. V naught t plus half a t squared x minus x naught is equal to this. Then this is 0, and half at squared, again, gravity is our acceleration. So if we let the apple fall for 3 seconds, then 1/2 times 10 meters per second for gravity times 3 seconds squared is equal to 5 times 9 equals 45 meters. So this would have to be a very tall apple tree if it really took 3 seconds to hit the ground. Or we could go in reverse and say, like, oh, imagine our apple tree is 10 meters tall. Then 10 meters is equal to, again, v naught t is going to be 0. There was no initial velocity, is equal to half gt squared. G is the same as a, but now we know the acceleration due to gravity is 10 meters per second. So then 20 equals gt squared, or 20 over 10 equals t squared, equals 2. So t is equal to the square root of 2. And that's how much time it would take for an apple to fall 10 meters on Earth. So we can do pretty cool stuff now with our second kinematic equation of motion. And that concludes this second video.